This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. Need a helping hand with your system's architecture? Software Mill will help you design high-throughput backends and event-driven solutions. We're a brand trusted by businesses and valued by employees due to our remote-first, transparent organization which gives back to the IT community through education and open source. Have an idea? Let's code together. Meet our Scala, Java, Kafka, and TypeScript engineers at softwaremill.com today.
Hello everyone, this is Felienne for Software Engineering Radio. Today on the show with me is Marco Faella. He's a professor of computer science at the University of Naples Federico II in Italy. Marco has contributed to the Parma Polyhedra Library, a well-known scientific library for symbolic manipulation of polyhedra. He has taught classes on Java programming, compiler construction, and software engineering to undergraduate and graduate students since 2005. Marco is also the author of today's topic, the book Seriously Good Software. Welcome to the show, Marco.
Hi, thank you very much for hosting me.
You're welcome. So your book is called Seriously Good Software. I think that's something that we all strive for. But what is good exactly? What do you mean by seriously good software?
I was trying to fill a gap that I felt in some types of computer science education. I have the impression that a lot of people come into programming with sort of a simplistic view of the job where you just have to find a way of achieving a certain task, achieving a goal that you've been given. And without a global view of the different forces, of the different qualities that software may or may not have, without a view of the trade-offs that are involved in writing good software. So that was the starting point for the book. And in particular, I think that a lot of curricula have very deep classes, and talking about especially computer science curricula have deep classes about specific topics like algorithms or operating systems and so on. But I think students may end up with a very vertical view of different topics and without a global overview of their relationships and how to compare and contrast these different techniques and when it's more appropriate to focus on one aspect versus another aspect of the software. So I try to provide a more horizontal, let's say, point of view across disciplines, across topics.
Yeah, I want to zoom into that vertical and horizontal a little bit because it might not be clear to all of our listeners what exactly you mean by that. So could you briefly point out what vertical and what horizontal mean here?
Yes. Let me give you a brief overlook of the book for our listeners. So the idea is the following. For this book, I have one single example that's developed in many different ways along the book. And in each chapter, I focus on a different software quality. For instance, I have a chapter on time efficiency, then I have a chapter on memory efficiency. And I keep refactoring the same example with respect to different objectives, with respect to different software qualities, and trying to emphasize the trade-offs between them. And so that's what I call horizontal. It's across this. It's across. You have a little bit of algorithms, of data structures, of operating systems, concurrency, software engineering, mixed together and compared on the same example. Whereas by vertical, I mean the classical computer science curriculum, where you take a full class on algorithms and you focus an entire semester, something like that, on big O complexity and the fastest way to do certain things.
Yeah, so what you're saying, I think, is that university often prepares students for really deep tasks like algorithms or databases, But what sometimes might be missing from a curriculum is how to apply them and how to make the right selection of what to use where. Is that a fair summary of the problem that the book addresses?
Yeah, absolutely.
So you mentioned this already a little bit, is that your book talks about different qualities that software can have. And while reading the book,
Mhm.
I found it hard to really define what a quality is. So can you briefly explain what is a quality before going into detail, of course, into the different qualities that the book talks about?
Sure. So by quality, I know it's a very general term. I mean any desirable property of software, any desirable property that a piece of software may or may not have, or may have to a different degree. And most of these properties are traditionally called non-functional requirements, but I'm not fond of this functional versus non-functional distinction, I have to say. I think most of these properties, they become so when you say that a property is non-functional, it sounds to me as if you are diminishing its importance. You're saying it's optional, it's non-functional. Whereas I think they're important. I think most of them, in fact, become functional properties beyond a certain threshold. For example, take time performance. Time performance is usually, in most systems, a non-functional property because you don't care whether your software gives you a service in 1 millisecond or 2 milliseconds. Most of the time, of course, it depends on the context, but most of the time you don't care. But still, even if it's even if it's a user-oriented service, that an interactive program, well, you may not care about 1 millisecond versus 2 milliseconds, but you certainly care that that service works within 1 second or works within 1 minute. And if you get that service in 1 hour instead of 1 second, of course, that very poor performance becomes a functional issue. And I think this applies to most so-called non-functional requirements. They can all become functional beyond a certain threshold if they're not properly satisfied.
Yeah, so to summarize, I think what you're saying is that qualities are quite related to non-functional requirements, but that you're not fond of this non-functional term because it seems to indicate non-importance or non-core to design, whereas you rightly point out that even something like reliability or time optimization can get functional once it gets too much out of hand.
Yes, it's a thin distinction. It's a requirement can jump from one side to the other quite easily. It's not clear cut.
Yeah, I actually think that's a really important distinction where we try to say this is functional and this is not functional, but it isn't as binary as that. It is
Right.
possible for properties to move over the spectrum of from functional to non-functional. So I was wondering, what was your goal in describing these qualities? So why was it needed to formulate the book in that way along these lines of these different qualities? What does that add?
First of all, I think it adds awareness to programmers, and of course the book is mainly intended for junior programmers or people fresh out of their school or their computer science or other kind of school, and organizing the book around these qualities. I mean, at least my intent was to make them aware of this different points of view on software, on these different requirements they may have to satisfy, give them a, let's say, in a way, a vocabulary of qualities to think about. So I'm very focused on this awareness idea. So before you can improve your software, before you can write good software, first of all, you have to be aware that there's a problem, or you have to be aware that there's different ways to measure, in the best case, or evaluate somehow your software. There's different point of views. Then, only then, you should be aware of the techniques that you can use to improve those qualities. And finally, on a kind of a third level, you should have the experience and the capacity to judge which quality to focus on among all those qualities that are always present somehow. So your software has to do its job. That's the correctness, that's the functional requirements. Then it has to do it in an efficient manner, and so on and so forth. So you have to be aware of these dimensions. Then you have to know specific techniques to work on those dimensions, to improve on those dimensions. And then finally, you or your coworkers or your boss have to have the vision to pick the right balance among these properties.
Yeah, so it adds a vocabulary to help people to make the right decisions. And you mentioned trade-offs also earlier in the show between all of those qualities.
One more thing. This idea is also an invitation to improve specifications, because I think often specifications focus too much on the functional aspects and too little on those other requirements. Whereas after the fact, perhaps during development, or perhaps after deployment, or at some point you realize that you overlooked some non-functional requirement that turns out to be important, and perhaps it turns out to be functional. It turns out to be crucial. So another direction where I hope the book can improve the standard practices is to improve specifications and push people to be more complete in their specifications, to include these so-called non-functional requirements in the initial in the software specifications explicitly.
Oh yeah, I really like that. I like that where you're saying this isn't only relevant for the process of creating software, it can also be important for the process of specifying and designing software. That's also where you can use these qualities as maybe something like a checklist even. Have we thought about all these 6 qualities?
Right. Yeah, exactly. As a reminder, well, what do we need about space efficiency? Do we need anything? What do we need about readability? That's a tricky part, but yeah.
So I think it's now time to zoom into the qualities. I would like to go over them one by one, where we can talk about what is the quality. Maybe you also have examples of code bases in which this quality did well or didn't well. So I would like to start with time efficiency. This is one that has come up already a bunch of times. There's really a difference between a query taking 1 second and a query taking 1 hour. So what is your definition of time efficiency?
Well, of course, time efficiency is simply achieving your task in as little time as possible. And I think it needs very little introduction to any programmer. I think most programmers are naturally interested in it, perhaps too much. And so putting it as my first quality is a kind of trick to get people interested in the book, because I know that so many programmers are just passionate and fascinated by time efficiency. I'm one of them, and I'm so happy when you manage to get a big speed up on your implementation. It's great. It's great for everyone. So it needs very little introduction. If you want a specific example or a small anecdote, just these days I was browsing Twitter, and a guy was complaining about the reaction time when he clicks on the right mouse button on Windows. In most cases, you get some kind of context-aware menu. So it depends on where you click. On your desktop, on your start menu, you get some sort of special menu when you click on the right mouse button. And he noticed that on a modern hardware, modern machine, sometimes you need to wait for, 1 second or 2 seconds to get that menu. And he thought that was crazy. And I think I kind of agree with him. I mean, it's one of the basic user interactions for Windows or any operating system these days. So it should be really fast. It should be instantaneous from your point of view. So the operating system and other software that's cooperating with it should cache those lines before you even click on the right button, and it should come out immediately. And so, I mean, it was interesting because then this guy went into a very deep debugging of the issue, and he was very capable debugger. He could find the source for this lag, and I think he posted some bug report on Windows, and I think maybe they're working on it, or maybe they already fixed it. I don't know, but that's a very simple example of something that we all interact with. And perhaps we're used to it. We're used to having to wait a couple of seconds to get that menu, but it shouldn't be like that. I mean, there's no reason why a modern, 8-core, 5 gigahertz machine should have you wait a couple of seconds to show a list of 10 items or 20 items.
Yeah, well, actually, you said in the beginning that time efficiency might be an easy thing to measure. However, I do think it's more complicated than it used to be. And now that you got me thinking of this context menu, I also recently was wondering why it was so slow. And then I realized that one of the reasons it's slow is that if you are connected to Dropbox, then Dropbox will go to the internet to see if you're actually connected. And if you are, you get extra elements in your context menu. You get like share this link on Dropbox or stuff like that. So something
Right.
where we might think, oh, this is a local operation and the operating system should be able to do this really quickly. Yeah, oftentimes nowadays, there's also some network connectivity in places where you don't necessarily expect it. So maybe time efficiency used to be easy because you could just look at your source code and sort of count the number of iterations in your for loop. But now that we have async await, so I think from my perspective, time efficiency was easier in the old days than it is now. Do you agree? And is this something that the book also talks about, the differences between measuring efficiency in your own code base and having stuff in different places?
That's a very good observation. So, in the specific case of the context menu, I'm sure there's a rather complex architecture behind it, because, as you mentioned, different programs can plug into that menu and add their own stuff. Still, I mean, you have the example of Dropbox checking on the internet whether it's connected or not, but perhaps then the architecture should be changed, or should perhaps I'm sure there's reasons to be like it is, but there's nothing preventing the architecture to have Dropbox check the connection beforehand, even before on the background, before you click. And then when you click, it just gives you the latest status. And if the latest status is unconnected, then too bad, it's unconnected. And you will click again, and maybe you are more lucky. But perhaps Dropbox could update every 10 times a second this little cache of items. Anyway, in general, about the book and what I do about time efficiency, I don't have the space to cover all these very interesting aspects you mentioned, like difference between doing something locally or having some uncontrollable lag in between. That's certainly an interesting issue practically. On the other hand, again, since the book tries to cover all of these different topics in a short number of pages, it's like a 300-page book, which tries to cover from algorithms to software engineering and so on and so forth. So it should be clear that every chapter is just a short introduction to the topic. So for every chapter, for every topic, for every software quality, I don't go into the details, but rather I give an overview of the topic. I apply it to my recurring example, and then I apply it to some other examples. And then I give pointers to other great books where readers can really fill in the details. So it's really works like that due to space constraints.
Yeah, of course we understand that even the book is limited, and this episode is even more limited in time. But if you could share with us just like one takeaway from time efficiency. What is the most important thing that our audience should realize when considering time efficiency of application?
Right. So there's it's not like a great discovery, but it's a little observation that perhaps is not present in traditional discussions about time efficiency. So the whole book, in the whole book, I focus on small code samples, not large systems. Just I focus on single classes. And most of the time, when you study algorithms in school, at university, you focus on a single input-output function. So you want to, given a graph, you want to output, I don't know, the shortest path from one vertex to another vertex. So simple input-output problems. Given this input, produce this output, and that's great. And on that kind of problems, you can apply all the asymptotic analysis, complexity analysis, asymptotic notation, and so on. My small observation is that in practice, even on a single class, so even in a very small unit, you have different methods operating on that class. And each method may have a different complexity. So you may have one method taking linear time, another method does something more complex, takes quadratic time, and so on. And my little observation is that sometimes you cannot optimize the complexity of all methods at the same time. Sometimes you have to choose. You can make one method faster at the cost of another method becoming slower. So that's another level of trade-off that you may have between different methods. Within a single quality, which is time performance, you may have to find a balance between the complexity of different methods. That's something that's shown in the book.
Great. Yeah, that is a good thing to take away, that you can magically make stuff better. Often if you make something better here, then you might actually worsen somewhere, something in another place of the code base. So I do think that's a good realization to make.
Yeah, and I make this observation on a small unit because that's the style of the book, but you can apply the same observation to larger systems where sometimes you can make one feature or one module faster at the expense of another one that's going to be slower.
Yeah. This also the same can be generalized from two methods to classes or two modules or two microservices that are at odds with each other.
Right.
Then the next quality is quite related, is space efficiency. So there too, I was wondering, what is your definition, and do you have another great anecdote of space efficiency and how it is impacting performance of code bases?
Right. So yes, space efficiency. Of course, by space I mean memory occupancy. So basic definition would be, well, okay, this is already a little bit trickier because a very basic definition would be to use as little memory as possible. That's a very simple definition, but that's usually not what you want in software development. So a better definition would be make good use of the memory of the memory you occupy. But of course, that's a better definition, but it's also more vague because what do you mean by good use? Let me here make my favorite example about space efficiency to clarify a little bit. So my favorite example is video games. I think video games are a fascinating pieces of software, not only as a player, but also as a programmer and as a professor. And in fact, I'm also teaching a game development class. So they're very complex software systems. And one of the characteristics of video games is that no matter how much memory your architecture, your device has, you can be sure that there are video games that people will write video games that will saturate that capacity, that will saturate the whole computational power of your device. And perhaps even when you come up with a new architecture, a new console, a gaming console, or a new device, even before the device comes out, there's already video games in production being produced that saturate the capacity of that machine. And the same can be said about graphic cards, of course. And this has always been true, like from the first video games like Space War from the 60s and the PDP computer to the latest games. It's always been like that. So video games really push the hardware to its limits. And in particular, they push the memory. They fill up the memory and they always have a lot more data that can be fit into memory. So in video games, you find that there's a lot of effort to exploit all the memory available, to push as much data as possible in RAM, as much data as possible in the video memory, and so on and so forth. And what happens when you try to squeeze as much information as possible into your memory is that you start to use special encodings for data. And that's something I also show in the book. So perhaps you have small integers. So you take a 32-bit integer and you put two 16-bit integers into one, even if your language doesn't have a short data type, for instance. So you start using crazy representations that squeeze as much information as possible into your bits. So you try to, in other words, you try to exploit every single bit in your memory. No bit is wasted. And that's very interesting. That's an interesting exercise. That's also a very extreme path that you should only take if you have no other choice. Because when you start using those crazy ad hoc representations, you lose on many other software qualities. You are probably losing readability because your software becomes tricky to read and understand, and therefore you're losing maintainability, you're decreasing your maintainability, and so on and so forth. So taken to the extreme, space efficiency is a very drastic measure. It really conflicts with other software qualities. On the other hand, in a normal program, you don't want to use too much memory without a good reason. So without going into those extreme representations, it's still good to have general understanding of how much memory a hash table takes compared to how much memory an array takes. In most implementation, a hash table, of course, it's much more efficient for many operations, but it's also many times larger than a simple array. Those are the kind of simple comparisons that every programmer should be aware of, regardless of the specific domain.
Calling all developers. There's no telling what you can create when you upgrade your data platform to InterSystems Iris. Are you ready to build the applications you want, however you want them? Are you ready to develop applications faster than ever? Collaborate, build faster, and deploy more efficiently. Tomorrow's next breakthroughs are waiting for you today. InterSystems Iris Data Platform. Ready, set, code. Start coding for free. Visit intersystems.com/try to try Iris.
Yeah, I really like this example of games because it's sort of reverse, right? Normally you have what you want to make and then it takes up the memory or the space that you have. But then for a game, it's just this is the memory and this is the hard disk size you have to fill, and you're just going to fill it as efficiently as possible. So I think that's an excellent example of a domain, a space where this space efficiency is just really, really core, and it maybe overpowers other dimension. One thing you just mentioned, and this is a nice segue into the next quality. You said sometimes being really space efficient, like using a very special encoding, comes to the detriment of readability. And readability is also one of the qualities that are in the book. So of course, here we also want to know, what is readability? And can you share another of those anecdotes or domains about readability and to contextualize it a bit?
Readability is a kind of hypothetical measure, because you can't really measure it in any easy way. But in principle, you try to imagine the effort needed to understand that code. particularly for someone who hasn't written it. But as we all know, as all programmers know, even your own code, if you don't look at it for a couple of months, it's basically as if it was written by someone else. You quickly forget the mental model that brought you to that piece of code, and therefore you basically have to start from scratch as if someone else wrote that piece of code. And the amount of effort you need to put into understanding that code is called readability, is related to its readability. And the readability, I think it's a very interesting quality, very different from the first two we talked about, so time and space efficiency, just because it's so hard to measure. At the same time, it's also very important, and the reason it's very important is that this readability is, in turn, is a proxy for maintainability. So maintainability means how easy it is to modify, to fix, to extend your program. And of course, every commercial software needs to evolve in time. It needs to be, it needs to have bug fixed. It needs to be extended, and so on. So having a code that is easy to read and understand is a good proxy to its future maintainability. The easier it is to read, generally speaking, the easier it is to modify it without introducing new bugs, because you understand it, because you manage to understand it and you know what you're doing. On the other hand, I noticed that it's at the same time, I think it's very important as a quality, but at the same time, there's little effort in academia and in general in schools, in programming schools, towards this objective. There's very little effort in teaching readability. And once again, that's because it's not a fully developed topic. It's not easy to measure, and there's no well-developed theory of readability. So what we have are examples. What we have are guidelines. And in fact, that's what I focus on in the book, because that's the best we have right now. I'm thinking about the famous refactoring rules by Martin Fowler's and Robert Martin's clean code guidelines. So those are practical, time-tested guidelines that are very successful in practice, but they don't constitute an overall theory. Okay, it's a set of guidelines. They work well in practice, and lots of people agree with them, and I think they're very valuable. But we don't have a systematic theory. I know there's people trying to measure. There's people in academia trying to actually measure readability. Sometimes I even read like scientific papers about taking brain scans of people reading code to try to scientifically measure the effort they're putting into understanding it. But I don't think these like extreme attempts are going to solve our problem. I think we need as a discipline, we need time to figure this out, to establish a consensus over what's readable code. And also, I think at some point it becomes a little subjective. So that at some point you cannot have 100% agreement on the rules of readable software. At some point, it becomes subjective. What's the better style?
Yeah, I think you're making lots of interesting points there that I want to follow up on. So yeah, definitely, of course, it isn't possible to measure the readability of code in the same way as space efficiency, as time efficiency. So maybe different things would be needed. And I think it's really interesting that you said, as a field, we don't really have a good theory for readability of code. I think I agree with you there, but I'm wondering, how would such a theory look like? What are the boundary conditions of such a theory? What is the thing? What is the thing we're missing there? Because you name some resources like refactoring. We have a bunch of things. So what are we missing?
Right. So let me mention a couple more things that we do have that, of course, you're well aware of, but let me mention them nevertheless. So we have a lot of proxy measures like cyclomatic complexity, method length, simply, We say that methods should be short, no more than, 20 lines, something like that. So lots of people have proposed different metrics. So it's numbers. It's something easy to measure. And then they try to connect these numbers, these quantitative, objective measures, to some other independent measure of readability, like asking someone after he or she has read a piece of code. So they ask them, how easy was it to understand? Or maybe they ask them, what does this code do? Please describe it or answer this question about the code, and so on. And they correlate these measures to the answers, to the questionnaire, to the answers given by the person. I think that's a very reasonable way to proceed. And I know that we have some results, even though, you're comparing something objective and measurable. Okay, that's everyone agrees what's the cyclomatic complexity of a given function. Okay, you just count the number of nested loops, nested conditionals, and so on. But on the other hand, you are comparing it with subjective judgments made by people, which means that sometimes one paper will claim something, and then another paper can claim almost the opposite because it asked the questions in a slightly different way to their subjects, or maybe the people answering the questions are different, have a different level of experience. So it's very hard to reach a consensus this way. But I don't see any other way to move forward. I think it is the right way, but we need time to establish standard protocols for these experiments. Then maybe we can move towards consensus about what are the best metrics, what metrics correlate the best with actual readability, with people's effort to understand code.
Yeah, or if I may offer an alternative theory or an alternative suggestion, maybe we should accept that these two qualities, or time and space efficiency, and on the other hand readability, are just different things. The philosopher Thomas Kuhn has this idea of incommensurability, that it's just impossible to measure two things with the same framework. And I think maybe one of the mistakes that people make here is that they try to reduce readability to also being a number, whereas an alternative way could be just to accept the fact that some things can be measured in a number and other things are vague, like, is this art piece nice? Well, it depends on a number of things, including personal taste. So we can try to make the one more numeric, or we can try to accept that maybe it isn't very numeric.
Yeah, I agree. Yeah.
And to move on to another quality, you also have the quality reusability. And reusability might suffer from the same issue as readability, that reusability is also hard to quantify. So again, I want to hear what your perspective is on what is reusability, and how do we measure it? Should we measure it? And if we want to, how would we do that?
So by reusability, perhaps also generality is a good word for this quality. I mean, how easy is it to take your implementation? And once again, I focus on small units. So let's talk about a single class. How easy it is to pick your class and put it in a partially or completely different context, in a different system, and make it useful there. Make it useful in another context. So my perspective on this is that focusing on this quality, first of all, is simply a great opportunity to learn something. So what I mean is it gives rise to very interesting programming exercises for people who are learning. For example, you can tell them, pick some class that you designed and turn it into a library. That's the most reusable. That's what we call completely reusable code. We call it a library. That's the code that's meant and intended from day one to be put in completely different contexts and still be useful in different contexts. So I think that's a very useful exercise for people learning to program. And because what you do, and this also happens in the book, is that you take this class. It has some data. Of course, you have to pick the right class. You have to pick a class that's amenable to being generalized. But if you pick a good class, then this class will have data, of course, will have operations, methods. And if you think about turning it into a library, you'll probably want to generalize the kind of data it supports, it contains. And then, of course, you want to generalize the operations. So what you end up doing is probably start from some concrete data types that are in the class. And you're probably going to replace them by type parameters. So you're going to use generics in Java terms or templates in C++ language and so on. And then you have to generalize the operations. And that's also a very useful exercise because you probably end up using interfaces, complex interfaces to represent what this abstract data type is capable of doing. And therefore, you'll end up using what are in Java called the bounded type parameters, bounded wildcards. So these pretty advanced language features that you don't get to use every day. In this kind of context, they will come handy. I think also C++ is adding this year. C++ 2020 should add something called traits or concepts. Maybe are they called traits or concepts? I'm not sure. That's related to this. That's a new kind of abstraction to generalize, to have a very expressive way of generalizing operations to multiple data types. So it's something that leads to using interesting and advanced language features that's useful for learners. Whereas in practice, on the job, I think that the situation is quite reversed because in practice, I think programmers are too keen to generalize their software. So most programmers are known to overgeneralize their software. Whereas in practice, on the job, when you have little time to achieve your goal, it's perfectly fine to write your context-specific class in a rather non-reusable way. So you should distinguish theory and the learning stage from, in this case, in most cases, with reusability, I would be careful about pushing reusability in practice, like on the job. Unless, of course, you are actually developing a library, then that's your primary goal. Reusability should be your primary goal.
Well, actually, I really like this frame of thinking. I think it's a really great question you could ask to students, but also people within a company. If this would become a library, what changes would you make now? And just to get people in the mindset of reusability, this might also enable reuse. If people would write their code in a more reusable way, then maybe more reuse would happen. So this is, I think, for me now already the highlight from this interview, because now I'm thinking of my own code base. I'm like, oh, but what if part of this would be a library? Then what changes would I make? So I actually think that's a really, really good way, and also a concrete way of.
I think designing libraries is a lot of fun for experienced programmers, but it may be a nightmare for junior programmers.
Yeah, but then it is a nightmare that, they need to get used to at one point, because you are going to release something either as an open source library, or there will be someone in your company that says, oh, you've done this before. Can I look at your code, or can I reuse your code? So it is good to practice it, because it might occur. It's likely to occur later in life.
Once again, when I say maybe a nightmare to junior developers, once again, I mean, it's not their fault. I mean, it's our fault as educators. I think that's another area where, in my experience in academia, we don't put enough stress and focus on designing good APIs, which is a crucial part of designing a library. We focus a lot on designing algorithms and implementing them. That's great. And on good data structures, it's also great. But I think we focus too little on APIs and larger scale issues or reusability issues.
We have 2 more qualities left, but this was actually one of the questions I still had on my list. So let's zoom into this a little bit more, because Why don't we teach that? I mean, you're a professor and I'm a professor. We have limited power to change this. Why do you think it is that most universities, also like my university, why don't we teach this? Like, is it too hard? I don't even know myself why I don't pay more attention to this.
Well, obviously, we have little time, right? So we have to make a choice, and I think a lot of it is tradition. So some areas like algorithms, and I mean, I'm totally fond of algorithm theory, and I've also worked research-wise on different types of algorithms. So I completely appreciate the area, and algorithms and data structures. They have first of all, they have a somewhat longer history than software engineering. These other concerns we are talking about, like good APIs and reusability, they would be called software engineering topics. And software engineering is a little younger than the more established areas like algorithm and data structures, I would say, because software engineering came with large systems, and large systems took more time to be developed than single algorithms. So there's tradition. There's areas that have a stronger tradition, and also those areas are more mathematical, and therefore they have a more developed theory or overall organic theory, and that's somehow easier to teach and also easier to test.
Yeah, I definitely think that testing has something to do with it. It's also easier to create examples for algorithms. Like, here's a 2 by 2 matrix, and now you have to multiply it with something else, or here's a maze, and you have to find the shortest path or the best way to run
Yes,
through this
and
maze.
everything is simpler in the sense that it's easier to compare to algorithms. You have all the structure. You have asymptotical analysis. It's precise. It's mathematical. It gives you an exact answer to the question which of these two algorithms is better. Whereas if you're asking which of these two APIs is better, that's a completely different matter.
It comes back to the measurability. That
Right.
also, when the student has solved the solution, we can say you have to do this within 5 seconds. Otherwise, your answer is wrong, or you can just use 10 megabytes of memory.
Mm-hmm.
Whereas with readability, it's way harder to judge, and maybe the student has really good arguments to do something in a certain way, and then
Yeah.
sometimes you might even be convinced. I mean, I've had discussions with coworkers where I was really like, "Why would you do it like this?" And then they say, "Well, because this," and you're like, "Oh well, this is not my opinion, but this is actually also a reasonable standing." So it might really have to do with this measurability as well, where it's just really hard to judge if a student is doing it right. And then in addition, of course, also the things you mentioned, lacking a good theoretical framework, probably lacking enough faculty that have enough understanding of this to teach it, and a short history maybe. They're probably all contributing to this.
Yes, I agree.
But then now, luckily, there's your book. And then if students have graduated and they still miss some of these qualities, we could say, well, what you should read is this book. And then let's come back to the book a bit, because we also want to talk about the other two qualities that we haven't talked about. And one of them is reliability. And I think reliability is interesting because I think it falls a bit in between the things we've discussed. Because in a sense, reliability is measurable. And you can say this server is up for 99.9% of the time. But on the other hand, it is harder to predict because we can't really calculate how often the server is up, because it might go down tomorrow for 10 days and then everything is different again. So reliability is a little bit in the middle. So what do you consider to be reliability? And please give us another juicy anecdote where stuff went wrong, because we love to hear that.
So I agree with your assessment. It's somewhat in between, because you can basically you can only measure reliability after the fact, but that's kind of too late. You'd like to measure it beforehand. And once again, you have some proxies here, some proxy measures that you can take beforehand. For example, testing coverage. is the measure that comes to mind. That's a proxy that you can measure before deployment, that it's a rough indication of reliability. It's one of the few things you can measure that's related to reliability, at least. So in the book, I take two different points of view. So I have two chapters about reliability. One is called Reliability Through Monitoring. And by that, I basically mean what's commonly known as defensive programming, or rather an expanded form of defensive programming. Because usually by defensive programming, you mean checking preconditions of methods at runtime. Basically, that's the basic version of defensive programming. But that's only a part of a larger framework that's called the design by contract, of a more general idea. And within this idea, you also have invariants, class invariants, and you have postconditions. So if you're really serious about reliability and you want to achieve that through monitoring, so through online checking that everything is going fine, then you may want to also check invariants while the program is running, and you may also want to check postconditions while the program is running. So every method checks that it's called with the right parameters, that's its precondition. Then it checks that the current object is in the right state before it starts, that's checking the invariant. And then after the method finishes its job, it also checks that that the method itself has done its job properly, which sounds kind of crazy because you're writing both the method and the procedure that checks that the method is correct. But sometimes it can be useful, but it's very expensive in terms of both time and space most of the time if you want to add all these checks. So this kind of extreme defensive programming is reserved for special contexts where, let's say, safety critical applications. It can be software for an industrial plant, software for the automotive industry, health industry. Those applications where a bug could be catastrophic, could lead to loss of life or loss of huge amounts of money, huge damage. And in this respect, since I'm talking about safety critical software, let me also mention that you can, speaking of these reliability techniques, you can also have one step further, which is static analysis and the software verification. That those are techniques that I've worked on research-wise, where you actually analyze the source code without running the software, and you try to prove formally, mathematically certain properties. And that's something I only briefly mention in the book because it's a very niche, specialized area. And then in the book, I moved through testing, which of course is the main validation technique everyone is using, because it's the most effective, practical way to catch bugs. And once again, as with all chapters, I have a short page span. So and testing has since it's so widespread, there's a huge literature on testing techniques, tips and tricks, and so on. So my chapter is just a brief introduction to unit testing techniques, because I'm always focusing on a small unit of code. And then I point to deeper and wider treatments and other books where you can get the details.
Yeah, but I think what you mentioned here is really interesting, that if you take really good care of reliability, that comes at the cost of time and space efficiently being increased with all of these runtime checks. Whereas you might be more efficient if you check less, and depending on your domain, as you mentioned, healthcare might be something where you really want to have that reliability. Whereas a game, for example, there space is more important, and then okay, maybe sometimes it crashes, and that's too bad, but that's a whole different situation. So it's interesting again how these qualities are they all have trade-offs with each other.
Exactly. Yeah, there's trade-offs everywhere. That's computer science.
Yeah. And then the final quality that you mentioned in the book, which was somewhat surprising to me because it's so detailed, is thread safety. So readability is like this super generic concept that you can apply to almost everything within a project. Yeah, the readability is not even limited to code. It also holds for documentation and APIs, as we talked about. But thread safety is so specific. And I would say it's somewhat related also to reliability. So why did you decide to make thread safety its own quality rather than integrated it into reliability?
Right. Yeah, you're absolutely right. So thread safety stands out as a little different than the others. And first of all, as you say, at first sight, at least, it's more specific than the others. It's like up until a few years ago, it would have been considered really a very specific quality. But these days, as you know, more and more software is inherently concurrent. And that's because of hardware development, where every machine is concurrent these days. It's actually parallel these days. And computers are not getting faster, not getting much faster in a single core point of view. So more and more software is becoming concurrent. So I think thread safety is going to become more and more important and should be considered almost as important as those other qualities. But of course, it's a part of reliability. So thread safety is about having a class able to having your class able to be used by several threads at the same time without data races, which means without unexpected behaviors, without getting into an inconsistent state. And also, I have to admit, another reason why I put it there is because it fits very well with my recurring example. We haven't talked about it. I'll just say a few words. The recurring example is a simple, I hope very intuitive water container example. You have a system of water containers. You can pour water into one container, and you can connect different containers with the so-called pipes. With imaginary pipes. And when you pour water into one container, this water that you pour should disperse equally among all containers that are connected to this one, among all containers that you have previously connected to this one with pipes. And that, I think, turns out to be a very interesting example. And it's very tricky to make it thread safe. So I have to admit, another reason why I chose this particular quality, besides the fact that it's becoming more and more important every day, is that it fits very well with this example because it's very tricky to make this water container class thread safe. And it allows me to talk about different synchronization techniques, including lock-free synchronization, which is a pretty advanced topic.
So the final thing I want to talk about, and this is people that listen to my episodes often, they know this topic always comes up, and that's the topic of different programming languages. So you mentioned these qualities, and the tips in your book, are they as applicable in, let's say, Haskell as they are in Node.js? Or is it the case that they fit a little bit more with certain languages or paradigms than they fit with others?
Right. So on the positive side, I would say that the overall message of the book is completely general. And the overall message, as I said several times, is about being aware of these different forces that pull your software in different directions, being aware that you're always choosing a trade-off. You cannot optimize all of them at the same time. There's trade-offs, as usual in computer science. You have to pick a trade-off. But before that, you have to be aware of these different dimensions of quality. And this, I think, is completely general and could be useful to someone programming in any language. The specific techniques, on the other hand, that I describe in the book are mostly about object-oriented programming languages. So not just Java, but certainly C#, because that's, as you know, it's very similar to Java. And in fact, I have little sidebars here and there in the book relating my Java techniques to their C# counterparts. But with a little effort, most of those techniques can be used and applied as they are in, I would say, any object-oriented language. If you move to a completely different paradigm, if you move to Haskell or functional programming or, I don't know, logic programming, then of course the qualities are still there, but the techniques you use to optimize those qualities, to improve those qualities, are quite different.
And do you think some programming languages also make inherent decisions of some qualities over other qualities?
Yeah, sure. Different languages are useful for different things, which means that they emphasize some quality over others. For example, Java and C Sharp, the two languages that are explicitly mentioned in the book, they were born with one of the main design objectives of those languages was simplicity and ease of learning. So, which translates to having a pretty good readability and also pretty good reliability. For example, just because they are garbage collected, that's somehow improves, it tends to improve reliability of the code. Of course, that was one of the design objectives 20 years ago when Java started. But of course, then it evolved. And nowadays, it's not as simple as it was 20 years ago. So it moved a little bit away from its initial simplicity. Now you have all new stuff to stay modern and to stay modern in the face of new languages. Of course, there's kind of a competition between different programming languages. On the other hand, to mention another object-oriented language like C++, C++ has a very different objectives, very different history. So it aims at succinctness, it aims at the highest possible performance in line with its predecessor C. And so it tends to, you can achieve the highest possible performance. You can basically write software as fast as the hardware allows, but you may lose you lose some readability, for example, and therefore some maintainability. So a simple way to look at this is to look at this, the difference between C++ and Java and C Sharp is look at the amount of symbols they use. So in C++, you have a lot more symbols. You have a lot more meanings for the symbols, like colon, semicolon, or dot. A lot more meanings for the symbol. And in fact, you even have operator overload when you can give your plus and your minus any meaning at all that you want. So there's lots of meanings for symbols that helps succinctness, but it tends to decrease readability because you read A plus B and you don't know what that plus means. You have to go figure out what the plus between those two objects means. That's a simple example. And then, of course, there's thousands of languages focusing on different things. Like most functional languages have very strong type systems, and those type systems tend to improve reliability once again. Some people say that if your functional program compiles, then it's quote unquote correct. So that's the experience of many people programming in functional languages. You know, you have your type system is so powerful that your compiler can check a lot more things than an object-oriented compiler. And so you have a lot more checks done beforehand by the compiler and a lot fewer runtime errors. And of course, you have more specific languages like, let me mention just one example, like Go, Google's Go language, which has some special machinery for concurrency. So it certainly helps make thread-safe software, for instance, because it has this special communication channels between threads that help avoid race conditions and so on. Of course, there's the list goes on and on.
So to summarize, the trade-offs between these qualities are language independence. They always exist.
Mm-hmm.
However, if you're choosing a language, then one language might value a certain quality, like Go might value something and Haskell might value something else. Well, some languages might value speed, some languages might value readability. So in choosing a language, there's definitely differences, but once you're in a paradigm, there will always be this trade-off between space and reliability, and these things are almost always at odds with each other, right?
Yeah, indeed.
Great. Well, that I think we covered everything I wanted to ask. Do you think there's anything we missed? Anything that you wanted to add to this episode?
No, I think it was great. I really enjoyed our discussion. It was great. I think it also helped me clarify certain points.
Great. Well, thanks. We'll make sure that we put a link, of course, to the book in the show notes so people can check it out if they want to. Are there any other places on the internet where people might want to follow you or keep up to date with other things that you're doing?
I mostly use Twitter and my homepage. So if people Google my name, they will get pretty quickly to my homepage, and then they can also find my Twitter handle.
Yeah, we can also add those to the show notes. So your Twitter handle and your website, we can make sure that they're linked with the episode so people can find it easily.
That's great.
Well, thanks for being on the show.
Thank you very much for having me.
This is Felienne for Software Engineering Radio.
Need a helping hand with your systems architecture? Software Mill will help you design high-throughput backends and event-driven solutions. We're a brand trusted by businesses and valued by employees due to our remote-first transparent organization which gives back to the IT community through education and open source. Have an idea? Let's code together. Meet our Scala, Java, Kafka, and TypeScript engineers at softwaremill.com today. Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.